Hello everyone, welcome to Learning Express YouTube channel. Today in this video we will continue the CTQ series, the question 9 part 3. So in previous two videos of CTQ 9 part 1 and part 2 we have discussed all 6 circuits. In the first video 4 circuits where we have discussed about the gain calculation and what is the output swing for the varying input from 0 to VDD. And in the last video we have covered rest 2 circuits, and now in this video we will see the noise analysis for any of these 6 circuits, random circuit, then how to analyze it. So we'll take the circuit one by one, and what is the way to analyze in terms of noise. So let's start from the circuit 1. This is the first circuit, second, third and fourth. Okay. So we'll start the fundamental of noise analysis for any random circuit. Okay. So if there is any block, in general, if there is any block, what you will see, if there is an input and output is there. For noise analysis, we'll simply do, it can be a gain block or the GM block. We'll calculate the short circuit noise current. First step is we'll calculate short circuit noise current at output. Calculate short circuit noise current at output. Second, while we are calculating this short circuit noise current, short independent sources, independent voltage sources, or input voltages, open current sources, independent current sources. Okay, so these are the two things that we have to do. And after that, once we can calculate the noise current, short circuit noise current at output, then we have to refer it to the input. So refer this short circuit current quantity, noise current quantity, to the input. Okay, so if we want to refer any current quantity to the input, and what we do, if there is any block and there is a current at its output which is ISC, and if I want to refer the equivalent value of this short circuit output current as the input, then what we will do, we will divide this quantity with the GM of the circuit. So what I can say, if I have ISC and I want to find V in, then what we will do, simple, V in is what, this short circuit current divided by GM. So what we can see, this output short circuit current is referred to the input by using the GM of this particular block. And same, if there is a gain block or the same block is there, then if I am calculating the output voltage noise, suppose noise voltage, this is a noise current, I will say noise current, this is a noise voltage, V in N, this is noise. So okay, this is a noise voltage. So if there is a noise voltage at the output, and if I want to refer this noise voltage to the input noise voltage, which is IIN, then what we will do, we can simply find it like using the gain of the block, using the gain of the block. So the concept is very clear. For any random block, if there is an output current and we want to find its input voltage and divide it by the GM, and if we have the output voltage and we want to refer it to the input in terms of voltage, then divide it by the gain of the block, voltage gain of the block. Okay, so in this way we can refer. Now we will see these circuits. Okay, how to extend this concept to the circuits. Okay, now first circuit is this simple, common source amplifier with resistive load. Okay, so this is a common source amplifier with resistive load. So I want to calculate the noise contributed by each and every element and its effect on the output, then we will refer it to the input using the gain. So first we will see what are the noise sources here. So noise sources, there are two noise sources. RD itself is a noise source, and this M N is your noise source. Let's say this is a Mn. Okay. So for RD, for any resistor, if there is any resistor, suppose R is there. If this is a noisy resistor, then we can extract it, the noise source out of it. How? We can model the noise source as a voltage in series, which is a VNR, and this resistor in the series of it. Now it is a noiseless. This resistor is noisy, and if we are extracting this noise source out of it, then this is a noiseless. So in series of this resistor, we can write the noise source, and other way, in parallel of this resistor, we can model the same noise source using the current element. Okay, so this is the noise current element, INR average, but this R is now noiseless. Okay, this is now noiseless. So what we will do here now, this VNR is what? VNR is what? 4 KT R root. So simply, usually we write the noise in terms of mean square value, which is the noise power, is a KTR. And for finding noise current, mean square value of noise current, it is nothing but this 4 KTR, which is nothing but voltage mean square divided by resistance square. Because voltage divided by resistance is current, but here the current is square and voltage square. So resistance square is used to divide it. So 4 KT by R. So this is the noise current, mean square value of noise current of resistor R. Here we are using the RD, so we can simply write it here RD instead of R. Okay, so this is for any in general resistor. This is the expression for noise. Now the other expression that we want to see for this means noise sources. One is a resistor. Resistor is done. Now second, this is a 1. This is a 2. Mn. So for the Mn, any transistor, we can model the noise as a current. Okay, so this is my transistor. I can model a current noise as like this. So this is your INM. What it is? It is nothing but a 4 KT gamma G of the transistor root. So the mean square value for this is also like, remove this underscore, sorry, root. So gamma GM. Gamma in general we use 2 by 3 in some cases. It is an empirical value, not recommended what to use, but in general somewhere it is used as a 1 also and 2 by 3 also. So usually we use it at 2 by 3. We can write it. So now here this transistor is noiseless. Now it is noiseless. Previously it was a noisy transistor. When we extracted this noise current source out of it, it is a noiseless. Other model of the transistor noise is a voltage. In terms of voltage, we can model it. Okay. Other way we can model in terms of voltage. How? We can write it. This same transistor can be written as series voltage noise at its gate. What is this value? This value VNM, I will say, this is nothing but it is a 4 KT gamma GM root of it divided by the GM of this transistor. GM of this transistor. So if we have to write this thing as a mean square value, then what we will write? Remove this square root and write the square. So this is cut down. So what you can see, 4 KT gamma by GM is a mean square voltage. Okay, so what we are doing here for the transistor, you can see for the transistor we are also referring this short circuit current at its output, which is nothing but a noise current. Here we are referring this noise current using the GM of the transistor to its input, which is nothing but a VMN. VNM is noise at the gate of the transistor, which is the mean square value, nothing but divided by the mean square current at the output by GM square that I told you previously. Okay, so now exactly we'll see how to calculate the noise for this circuit. Okay, so this is my RD for that. Now BDD for the noise calculation, I'll assume it to the ground, and also input I will short it because noise analysis short it. So this is my short circuit output current, ISCN. Okay, so we can consider two noise sources here. One noise source for this that I'm representing using star. But if I want to give the direction, I'll give this direction with this INM underscore. Sorry, average of it. And the second current, if I want to give this direction, and intact with the direction only. Anyway, direction is not important for the noise. Once you considered any direction, stick with that throughout your calculations. So this is your INR. Okay. So what we can see, if one by one using superposition principle, if I consider the noise source of transistor only, then what we can see RD at time being noiseless. I have considered direction downward. This is my INM, and this is my short circuit noise current ISCN. Let's say it is 1 due to the transistor only. So what we can see here, just to do the proper KCL analysis, this node is shorted and this is also incremental ground. So the current flowing here is 0. And also GMVGS, there is a ground, means a gate is sorted for the for the transistor, source is sorted, and drain is also sorted. So no other current element is there. Only this INM is flowing. So what we can see, this INM is completely going through this. So ISCN 1 is nothing but equal to magnitude wise it is INM. I am not considering the direction because direction is not important for the noise. In case whatever I considered here, in that manner I can write it the negative, but it is not important that. So because mean square value, again you can write the mean square value for this is INM square. So it is 4 KT gamma GM, GM of the transistor. So this is the noise current coming at the output due to this amplifier only. Sorry, due to this transistor only. Now we'll consider, this is a one case. Now we will consider the resistor only. Okay. So this is 0. If we are considering this noise current of resistor only, and let give the direction. Okay, this is a INR ISCN2. Okay, so again look carefully at this KVL and KCL analysis. You will see the gate is shorted, source is shorted to ground, and drain is also shorted. So no current component here, not even GM component, not even GDS component. Means okay, so no component of current here. Here also, this terminal is to ground, this terminal is to ground, so no current through this RD. So only this current INR is flowing through the short circuit current of output. So this is INR. In terms of mean square value, I can write it ISCN2. Take all the mean square value is INR square, which is nothing but 4 KTY and R, 4 KTR. Okay. So what is the total noise current? Total noise current at output is total noise current at output. Sum of the both. So it is 4 KT gamma GM plus 4 KTY RD to the RD. So this is the total noise at the output. Short circuit noise current at the output. The mean square value of short circuit output noise current. So now what is the input referred noise? So this can be written as ISCN out. Output short circuit noise current mean square value is 4 KT. Let's set it common gamma GM plus 1 by RD. Okay. So what is the input referred noise? Input referred noise. Input referred noise is what? If you have output short circuit current mean square, then what should you do? Divide it by GM of the circuit square. This is my input noise. This is a noise at input. Okay, input noise mean square value is an input referred noise. So the value will be, if I want to send noise at input, average value is nothing but output noise current divided by GM. And GM is nothing but a short circuit transconductance of the circuit. This GM is nothing but a short circuit transconductance of the circuit. GM is short circuit transconductance of the circuit. So here we can see the only component is here, this Mn. So this GM for the circuit, if we calculate using this ISC, and this is my Vn, then we can see the short circuit transconductance for this circuit is nothing but a transconductance of this device only. Okay, so GM of the entire circuit is nothing but GM of this N only. So what we can see from here, the noise at input average is nothing but ISCN at output, average noise current at output divided by GMN. So what you can see what it is 4 kt gamma. Let I write the mean square value so that the calculation has not any root term. 4 kt gamma gm, that gm is nothing but gmn only, gmn plus 1 upon rd, and refer it to the gmn square. Okay, so input referred noise mean square value is 4 kt gamma y gm plus 4 kt gamma, sorry, not gamma, 4 kt by rd, 4 kt by rd into gmn square. So what we can see from here, the conclusion of the story is here that if we want to reduce the noise, so what conclusion is? Conclusion: to reduce the input referred noise, to reduce the input referred noise, input referred noise, increase GM of the input device where we are taking the input. So this is the one conclusion. Then there are limitations on increasing GM are also there. What are the limitations on increasing the GM that we have to see? What is the GM expression in general? GM expression in general is 2 IT by V overdrive. Okay. So if we want to increase the GM, anyway we have to reduce the overdrive voltage. Okay. Reducing overdrive is what we are forcing our VGS near to VTH. It means we are forcing our transistor in sub threshold. Okay. Or toward the off condition. So this can be a bit challenging. So in some applications, it is desirable to operate the transistor near subthreshold or in subthreshold, but not always. So lesser this V overdrive is, and ultimately increasing your GM is a fine, but we cannot reduce the V overdrive much because the transistor is going near to the off state, which is subthreshold state. This is the one limitation. Other limitation you can think. So now let's move to the second circuit where we are considering the current source. Okay, so that circuit is very similar for the noise consideration with that circuit only. In this circuit, what we are doing, instead of RD, we are using a ideal current source. Okay, so we are using ideal current source, so no changes there. Only the current noise current of your device MN will come into the picture, and ideal current source, I am considering that no noise is contributed by this current source. So this expression for this circuit's noise is simple. The noise at the output, I am directly writing it, output noise current is what? Simply the current of your noise current of your amplifier, which is nothing but 4 kt gamma GM. And input referred version of this noise voltage is, what is the input referred version of this noise? Is 4 kT gamma GM by GM square. So it is simple, 4 kT gamma by GM. So the input referred noise for this circuit is directly the noise of your transistor only, because ideally no noise is contributed by this current. So I am considering no noise contribution by, no noise contribution by ID. Okay, this is the second circuit. Now for the third circuit, what you see, we have a PMOS. Okay, for the third circuit. So in case of third circuit, we have PMOS, and it is biased externally. BB is VDD. Okay. So for the noise analysis of this circuit, what we'll do, we'll again calculate the short circuit noise current at the output. So I'm just telling this in short. What we'll do, what are the steps we have to take? First, we have to make these things 0, 0, 0 means AC short. Because noise is nothing but a signal parameter. Okay. So one noise current is here, which I am considering the downward direction, which I call IN, noise of M1 average, and for this I will consider it upward. Usually I consider drain to source direction. Usually I consider, but it is not important or not recommended for the noise, but you can consider. And whatever direction you consider, is to good that throughout your calculation. So this is IN of M2, okay, upside. So what you can see, if I want to see output short circuit noise current, and what it will be, it will be IN M1 plus IN M2. Okay, so they are uncorrelated source. So what we will see, mean square value will be individual mean square. They are uncorrelated sources, so mean square value will be individual mean square values. Okay, so we can write directly. IN1 we know it is nothing but 4 kT gamma GM1 plus 4 kT gamma GM2. Okay, so what you see now, we are getting output short circuit current as mean square value of this as 4 kT. Let I say it common, 4 kT gamma is common, GM1 plus GM2. So this is the output short circuit current. But exactly, if you want to refer to the input, then what we have to see, we have to see the transconductance, short circuit transconductance of this entire circuit, and what it will be. The short circuit transconductance for this circuit is, again, do what you can calculate if you want, otherwise directly I will say it will be nothing but a transconductance of input only. So this thing we can see, this is your input, I am calculating short circuit transconductance. Okay, so this is my ISC. This is noise, it is not a noise current, it is different thing. This step is for calculation of a short circuit transconductance only. Okay, that's it. Yeah. Yeah. So what is the current generated here? We can see for the lower device Mn, or the M1, for the lower device only the current element is GM component, because we have the gate source, but no other voltage source is here. So this is GM1 V. Is there any other current component? Is there any GDS component? No, because drain is also zero. The source is also zero. For our above device, there is a gate zero, drain zero, source zero, everything is zero. So zero current is going there. So what I can see, this ISG is nothing but minus GM1 V in. So ISC by V in, which is nothing but short circuit transconductance of the entire circuit, is nothing but minus GM1, which is, I will say, as a GM only. Magnitude by it is a GM1 only, means input transistors GM is the only GM of the entire circuit for this structure, because above device is not contributing to the short circuit current in case of GM calculation. So the GM component is generated by the lower device, which is your input device only. So it is the entire circuit GM. So now we can refer the noise to the input. So input referred noise. What is the input referred noise voltage? It is simple. Vn input referred mean square value is what? 4 kt and gamma is also I'm putting it outside. Gamma. Okay. GM1 plus GM2. The output short circuit noise current referred by this GM of the entire circuit square. So it will be 4 kt gamma GM1 plus GM2 divided by GM1 square. So what we can see, 4 kt gamma by GM1, it will be 1 plus GM2 by GM1. Okay, so this is the input referred noise. Now, if you want to optimize, if you want to increase this input referred noise for this circuit, then what are the conclusions? So, yeah, gamma is of course 2 by 3. Conclusion, to improve noise performance, one, increase GM of input device, and second thing, reduce the GM of load device. Okay, so this is in general it happens, we have to increase the GM of input device and we have to reduce the GM of load device, and there are limitations for that also. In many examples, in many circuits, it is possible operate input device in subthreshold region. Operate input devices in subthreshold region. Subthreshold region, because in that region we have substantially high transconductance. Because in this region very high transconductance of high transconductance. Okay, and reducing the GM of load device is simple. How can we reduce the GM? So there are possibly few relations of the GM. If you want to analyze, you can see by your own. But I just am giving some conclusion here. GM is simple. 2ID by V overdrive. Keeping WIL as a some means value. Okay, I'm not writing what is the GM by WIL, but yes, for reducing the GM, what we can do, we can increase this overdrive. And increasing the overdrive means we are consuming more headroom. Increasing overdrive means consuming more headroom. It means swing problem. So this is the limitation. It means swing problem. Okay. And this is the one way. If you want to increase the overdrive voltage, we can reduce the GM of the loading device. Is there any other way to reduce this GM? What is the other relation of the GM? One more relation is 2ID K and dash WIL. This is also one relation. Can we do anything from here? Yeah. If we can reduce the current through the loading device, if we can reduce the current through the loading device, we can reduce the GM. But is it possible to separately reduce the current through the loading device? Because we want more current through this input device so that we can increase its GM. Okay, for increasing the GM of the input devices, we have two things. One is the current we can increase, we can reduce the overdrive. But we can reduce the overdrive up to the region where we are operating the device in the sub-threshold region. And we can increase the current in some limitation also, because power constraint is also there. Increasing the current means power constraint is also hit. So noise, more the current we want, lesser the noise we can get from the input device. But again, the problem is that power constraints. We can burn a current of required amount only because of the power limitation for the circuit. So there is a octagon. If you are known of this, the design octagon. If we are increasing, so let I touch this talk also. So there is a design octagon. From here itself, from this example itself, we can see What are the parameters that we have to consider? If we want to reduce noise, if you want to reduce noise, then what is happening? You have to burn more current. Burn more current. Burning more current means more power. More power is required. So ultimately, what we can see, nothing can be done without worrying others. So in analog design is all about considering all parameters and limitations simultaneously. We cannot increase current much, we cannot increase the size much, because other parameters like frequency constants will also be come into the picture. Because for example, if I want to reduce the GM of loading device, then what are the possibilities? From the relation we have seen, there is a current which is flowing through the load, and there is a overdrive voltage. And if I want to increase the overdrive, what we can do? We want to increase the overdrive, we can do one thing, we can reduce the size, fine, but we cannot increase the overdrive much because there is a swing issue. So okay, more power is required. So if we want to reduce the GM, then what we can see, again, for loading device, overdrive need to increase, and increasing overdrive means again swing issue. Okay, swing issue. So there are many issues associated with one particular change in analog design. So we have to think then which particular change has to be done and how it should be done. And depending on your budgets, what is the power budget, what's the noise budget, and other thing possible. So this is from the third circuit we have seen. Okay, more analysis you can do for this. Now let's say commit the fourth circuit, which is a diode connected device as a load. Now commit fourth circuit. So what about this noise of this circuit? Again, the fundamental is very clear. We will consider the noise sources and we will see the effect on the output short circuit noise current. Okay, so I'll consider this. This is a zero. It is zero. So overall short circuit noise current. Yeah. So one noise current is here, which is your INM1. One noise current here. So now we have to see what are the current components, or we have to simply apply the KCL at the output node. Here VGS is 0, so no VGS component. VDS is 0, so no VDS component. So I no IDS component, sorry. And for the out transistor also, there is a VSG 0, means VGS is 0, VDS is 0, so no other component for that circuit also. It means this circuit is noise contribution is same as the previous circuit. Okay, so what we can see from here, it is nothing but INM 1 plus INM 2, and both are uncorrelated sources, so we can write the mean square value of the noise at the output, that is called mean square value at the output, is nothing but INM1 square individual mean square values. So it is same 4 kt gamma gm1 plus 4 kt gamma gm2. So there is a no difference in previous circuit and this circuit in terms of noise. Okay, so they are same. So rest analysis of this noise optimization you can do. I should write the expression for the input referred noise mean square for this circuit as well. It is nothing but 4 kt short circuit transconductance you can calculate. So I will not tell you how to calculate here again. GM1, GM2. So the noise calculation is same for this circuit as well. And also you can see the short circuit transconductance is coming as the transconductance of input device only. Or you can see this thing also using drawing the circuit. Okay, this is a diode connected device. So only the current generated by this input device. If we are seeing the short circuit current, ISC, here everything is zero, so no current is flowing here. Means all three voltages, gate, source, drain, zero, so no current is going here. Only the current component here is GM1 V in. So this ISC is nothing but minus GM1 V in or I can say the short circuit transconductance for the circuit is again the input divided transconductance. So we can put this in the equation and we can see it is same as the previous circuit. Okay. So this is the discussion for the noise analysis of these four circuits and how we can optimize the noise and what are the limitations while we are optimizing the noise by burning the more current and by reducing the overdrive voltage or by increasing the overdrive voltage. And what are the limitations? String limitation is there, power budget limitation is there, many other possible limitations are there. So you can see there is a always existing means problems or issues with the analog design. Once we are increasing one thing, we are losing something in somewhere. Okay. So this is the discussion of noise in general. For the any circuit, we can do the fundamental analysis of noise by just considering the output short circuit noise current, and we can refer it to the input by just considering the transconductance, short circuit transconductance of the entire circuit. So this is the to the point because there are two devices only. Once you'll consider the more devices in the circuit with a stack of the devices, then we can see how to exactly calculate the short circuit transconductance of the circuit and how we can get the short circuit noise current at the output, and we can refer it to the input by using that transconductance of the entire circuit. Okay, so I think this is enough for this particular video where we are considering the noise of these four circuits. In coming video, we see the noise of rest two circuits, which is more important in terms of calculation. Okay, so this is enough for this video. Thank you.